Good day everyone. Today, we are going to present our project about the strength of materials in its real-world application through a bridge diorama model. Strength of materials is an important field of the study that helps us understand how materials react when forces such as tension, compression, bending, and torsion are applied to them. These forces affect the ability of materials to maintain their shape, stability, and safety in everyday structures like buildings, bridges, and roads. By understanding how materials behave under stress, engineers are able to design structures that are strong, durable, and safe for a long time. For our project, we created a simply supportive bridge diorama using popsicle stick and other materials to demonstrate how real bridges respond under the load. When weight is applied to the bridge, internal forces develop with the structure, causing the top part to experience compression while the bottom part experiences tension. This model helps visualize important concepts such as beam, bending, shear force, and bending moment in a simple and practical way. Through this demonstration, we aim to show the importance of strength of materials in ensuring the stability, efficiency, and safety of structure used in everyday life.
After planning the bridge design, the needed materials were gathered for the diorama. Popsicle sticks were used as the main structural members, representing steel trusses or concrete beams in real bridges. Wooden sticks served as additional reinforcement and bracing to improve stability. Styrofoam blocks acted as pin supports while rocks represented as roller supports. A styrofoam load was used to simulate the weight applied to the bridge. And glue stick adhesive represented the welded or bolted joints that connect structural members together. To build the bridge, the group first measured and arranged the popsicle sticks to form the main truss framework. Wooden sticks were then added for extra support, and the members were connected using hot glue. After placing the support at both ends, the simulated load was applied to observe how the bridge bends and responds to forces. This process helped demonstrate how real bridges behave under load and where failure is most likely to occur.
We began our test with a 200 kN load. At this stage, the support reactions are balanced at 196 kN each. The bridge handled this easily as the internal forces remain well below our material limits. The structure is stable and the truss is performing exactly as designed. Joint C and Joint G, the applied load was 96 kN each. Based on the analysis, these loads produce compression forces in members BC and FG, while members AC, CE, EG, and GH experience tension. The bridge remained stable because the loads were still within the allowable capacity of the structure. Using the computed load factor of 1.53, the estimated failure load at both joints was calculated as 147 kN, which means the bridge could still safely carry additional load before failure occurs. For part 2, at joint E, the bridge carried the highest applied load of 200 kN. This caused members DE to experience a large compressive force, while members BE and EF carried tensile forces of 163.3 kN. Since the center of the bridge experienced the greatest bending moment, deformation becomes more visible at this point. Using the allowable stress analysis, the estimated failure load at joint E was computed to be 306 kN, showing that the structure can still resist higher loading but is approaching its critical condition. For part 3, as the load approaches the calculated failure loads, the top compression members AB, BD, DF, and FH becomes the most critical parts of that structure because each member carries about 326.7 kN of compressive force. These members are highly vulnerable to backlocking due to excessive compression. Once the applied load exceeds the allowable stress limit, structural instability and failure are likely to occur. This demonstrates how increasing loads affect the internal forces within the bridge and highlights the importance of proper structural analysis in preventing bridge failure.
The bridge diorama successfully demonstrated the principles of strength of materials and structural analysis through a simple but realistic model. By applying loads to the bridge, our group observes how tension, compression, and bending can occur within a structure. The analysis showed that the bridge could safely support loads up to approximately 1.53 times the original design load before failure becomes likely. The project highlighted the importance of proper structural design, material selection, and load analysis in ensuring the safety and stability of engineering structures. Overall, the activity provided a clearer understanding of how real bridges behave under different loading conditions and how engineers apply these principles in practical construction and design.